In this video, we are going to be discussing the example 2.9. 45 grams of ethylene glycol is mixed with 600 grams of water. We need to calculate the freezing point depression and the freezing point of the solution. So basically, obviously, based on this question, it's quite obvious that this question is related to the depression in freezing point. So we've been given the following values. The mass of C₂H₆O₂ equals to 45 grams. Mass of H2O, water, is 600 grams. We need to calculate the freezing point depression. Obviously, we will have to use the different equations related to this. So delta TF is equal to the K F into M, where Kf is the the cryoscopic constant, and M is the molality. So obviously we need to calculate the molality of the solution, right? So the molality of the solution is equal to mass. Oh, sorry, actually not mass. I am so sorry. The number of moles of the solute divided by the mass of solvent in kilograms, right? So that is the calculation. And first of all, let's look at the mass of the water. We want to convert it from 600 grams to kilograms. So we will be multiplying 600 grams, or rather dividing it, dividing it with 1000 grams, kilograms, inverse. So gram gets cancelled. Then we get 0.6 kilogram. The reason we want it to stay in kilogram, there is a reason. If not, I would have been like, oh, let's just do it this way. The reason I want it that way is because if you look at your textbook, the previous page, page number 53, based on my textbook, it says page 53, you have the value of Kf and Kb of various solvents. The solvent for this particular solution is water. So the value of Kf for water is equal to 1.86. And the units are given on top. It is Kelvin kilogram per mole. And because of that, we want it to stay in kilogram. If not, we would have to convert this. And I think it's, let's face it, it's easier to convert the mass of water from 600 grams to kilograms than it is to figure this out. Pretty sure we can do it too, but I just feel like this is easier. Okay, so this is the mass of the solvent in kilograms. Next, we need to calculate the molar mass. Molar mass by now, molar mass of ethylene glycol. I'm pretty sure you know how to calculate that. So molar mass of C₂H₆O₂ will be equal to 12 into 2 plus 1 into 6 plus 16 into 2. And this gives us 62 grams per mole. The next one, we'll have to calculate the number of moles of C₂H₆O₂. It actually helps if you know the concept, like the mole concept and all of that, well, for this particular chapter. I would highly recommend going back to that one if you have time. It's just, I mean, the time I'm recording it, it's the beginning of the school year. You'll have time to just go back and look at it just because it's easier. And then you'll be able to understand all of this much more easily. There are videos for that. I think I started this channel with recording those videos long time back. So you have number of moles is going to be mass divided by molar mass. So 45 grams divided by 62 grams per mole. And this on simplification is going to give us 0.73 moles. We're going to be substituting this and this value to calculate the molality. So the molality of the solution is going to be equal to moles 0.73 moles divided by 0.6 kilograms, and that is equal to 1.2 moles per kilogram. Now all we need to do is calculate the value of delta TF. So delta TF is equal to Kf into M, where Kf is 1.86 Kelvin kilogram per mole into 1.2 moles per kilogram. So cancel. And this, when simplified, gives us the value of 2.2 Kelvin. Okay, now delta TF is 2.2 Kelvin. We know the freezing point. So freezing point of water at atmospheric pressure is, so we can say TF naught is equal to 273.15 Kelvin. Okay, so delta TF equals to, in your textbook again, this is given TF naught minus TF, where TF naught is the freezing point of the pure solvent and TF is the freezing point of the solution. So TF will be equal to TF delta TF plus TF naught. Okay, so we can just calculate it. So the value of the freezing point of the solution will be equal to the change in freezing point, which is going to be 2.2 Kelvin plus 273.15 Kelvin. And this gives us the value of, oh, I'm so sorry. Wait, I think I made a mistake somewhere. Also, the battery is dying. Oh, right. Sorry. So let's do that again. Delta TF equals to TF naught minus TF, right? So when this, okay, this goes here and this goes here. So you get TF equals to TF naught minus delta TF. There we go. Okay, so we just rearranged it and I rearranged it so wrong. So you get TF naught, which is the freezing point of the pure solvent minus the freezing point of the difference in freezing point. So you get 273.15 Kelvin minus 2.2 Kelvin because there is a depression in freezing point. The freezing point of the solution has to be less than the freezing point of the pure solvent. So this gives us 270.95 Kelvin. So basically, we were supposed to calculate the value of the depression and freezing point of the solvent, as well as the how much is the depression and freezing point, by how much. So we started with calculation of the molality, and to do that, we had to convert the mass of water from grams to kilograms because the value of Kf is in kilograms. Then we use the calculation of the molar mass and the number of moles, and then we were able to calculate the molality. From the molality as well as the value of Kf, we were able to calculate the value of delta Tf, and we know the vapor, the freezing point of the pure solvent, which is 273.15 Kelvin, and from that we were able to calculate the value of the freezing point of the pure solution. With that, we're done with this particular example. In the next video, we will be again continuing with the example problem.